Okay, going to be working on 11.3 partial derivatives, starting with number 7 and working through 31 odd. So let me write down number 7 here. We have a function of two variables, f of x, y, equals y to the fifth minus 3xy. I think I've got my microphone set right. I know in this room I get kind of an echo-ish chamber feel to the room, but I can't do anything, or to the audio, but I can't do anything about that. So, all right, so they're asking for us to find the first partial derivatives of this function. So we want to find two different things. Since there's two variables, we want to find the partial of f with respect to x, and we want to find the partial of f with respect to y. So let's start with the partial of f with respect to x. So what we're going to do is we're going to treat y as if it's a constant. So since this is the first example, let me just give you an example. If I just let y be, let's say 1, then this would become 1 to the fifth, which is 1 minus 3x times 1. And so if I took the derivative of this, the derivative of that, because it's a constant, would be 0, and then I would just really be taking derivative right here. This 1 would just be a number out front. So that's kind of the same principle we have here, except that we don't want to actually replace y with something. We just want to mentally remember that y is a constant. So y to the fifth power, that's a constant. Derivative of that is 0. Minus, okay, now y is a constant. It's attached to some function of x. So when I take derivative of that, the y will come with me. Okay, so y is going to be part of my answer. And then the derivative of negative 3x is just negative 3. So, or I have the minus already, minus, and then I'm just going to have 3 here. So the answer is negative 3y. Now the partial with respect to y, what we do is we do the opposite. We treat x like it's a constant and y like it's a variable. So the derivative of y to the fifth would be 5y to the fourth. And then minus 3 times a constant. So negative 3 times a constant, that's all a constant. That's going to come with me. Negative 3x. And then the derivative of y with respect to y is 1. So we just get a 1 there. So we don't need it. And that would be it. That's our partial with respect to y. Let's make sure that's all they wanted. Yeah, that's all they wanted. All right, that's number 7. Now the next few are going to work like that, and I'm not going to work out all these odds. Let me just get to something a little more interesting. How about 13? Again, we have a function of two variables. It's ax plus by over cx plus dy. So here, a, b, c, and d are all constants. All right, so that in the problem, no matter what, a, b, c, and d are constants. When we try and find the partial with respect to x, we're also going to treat y like a constant. So how do we take the derivative of this? Well, if y is a constant, that's a constant. And this right here is a constant. And so what I have is some function of x, ax, up here, and then some function of x down here. When you take derivative of a function over a function, you have to do the quotient rule. So I'm going to take first the derivative of the top with respect to x. So the derivative of ax is a, plus derivative of by is 0, because that's a constant, so just a on top. Then times the bottom, so I'm doing quotient rule. Minus now the derivative of the bottom. The derivative of cx is just c, plus the derivative of dy, which is 0 because d and y are both constants. Now, continuing with the quotient rule, that's derivative of the bottom times the top, which is ax plus by, and then all of this divided by the bottom squared. And then we can try and clean this up a little bit. I'll distribute my a through here. So a times cx plus a dy, and then distribute a negative c through here, so minus c times a times x is the same as a times c times x. I don't really need that dot there. A cx, and then over here negative c times b times y, I'm going to put b cy, that, and then all over the bottom squared. So cx plus dy squared. Notice my a cx's cancel, and then I have a dy minus b cy. The most I could do there is pull out a y maybe, but even that wouldn't really necessarily be something you have to do. That's it right there. So there's your partial with respect to x. Now I'll do the partial with respect to y here. So the partial with respect to y is going to be the same story, except this time we're going to treat x like a constant, which makes this a constant and this a constant. I still have to do the quotient rule. So the derivative of the top is going to be 0 here, because that's all a constant, plus derivative of b times y with respect to y is just b. So b, and now times the bottom, cx plus dy, minus derivative of the bottom, remember this is a constant, so 0 plus derivative of dy is d, and then times the top, ax plus by, all of this over the bottom squared, cx plus dy squared. And then if we do this, let's see, do we get any canceling here? We have on the top, if we distribute through here, bcx plus bdy, distribute here, minus a dx minus b dy all over cx plus dy squared, and we get those to cancel. So we just have on the top this minus this, but they both have an x, so I can pull the x out. bc minus ad over on the bottom cx plus dy quantity squared. There we go. So that's number 13. Let's see, they in the answer solutions, they do factor out that x and they do factor out that y. All right, moving right along. Let's see what else looks interesting here. 17 looks interesting. Okay, so 17 is r of pq. So r is the name of the function. It's a function of two variables, p and q, is equal to arctangent of pq squared. So now we have some composition. We have an inverse trig function, and inside of it our argument contains both of our variables p and q. So what we're going to first do is try and find the partial of r with respect to p. Since we have two variables, our function's name is r, this is one of the possibilities. The other one would be the partial of r with respect to q. So if I do this, I'm going to hold q as being a constant. So q squared here is just some number, and that's going to be multiplied times p. So first thing I have to do, what is the derivative of arctangent of something? Well, it's back from Cal 1, it's 1 over 1 plus the argument here, pq squared, quantity squared. Then times, because of the chain rule, derivative of what's in here. And again, because q squared is a constant, I'm just going to look at p. What's derivative of p? With respect to p, it's 1, but then times the constant. So I just get q squared, which is 1 over 1 plus, we can go ahead and square this, p squared q to the 4th. Oh, 1 over. Let me move the q squared on top. There we go. So that's our partial with respect to p. Now our partial with respect to q is going to look very similar, because now what we're doing is we're treating our p like it's a constant and q is the variable. But I still have to do the chain rule, so I still have to start out with this part. This doesn't change, but this part does. So derivative of this, so p is a constant, so I'm just going to cover it up. Derivative of q squared is 2q, but then I have a p, so it'll be 2pq. So the derivative of q squared is 2q, but then I have to bring the p with me because it's a constant. And just put that on top. We get 2pq over 1 plus p squared q to the 4th. So that's it for number 17. All right, what else looks interesting here? Let's look at 19. 19 is kind of interesting. We have capital F of xy is equal to the integral from y to x of cosine of e to the t dt. All right. Oops. that's not good notation. E to the t dt. All right, so what are the partials that are possible? First is partial with respect to x, because I have two variables here. Partial of f with respect to x. So you look at this and you remember that, if you take the integral of something, let's say with respect to x, but you differentiate it with respect to x, the integral and the derivative are like inverses of each other, so they basically wipe each other out, and all that would come out is what's in here, the integrand. So when we do this, we can do something similar. What we're going to do is we're going to first imagine taking the derivative, the partial derivative, okay, I'm using some different notation, with respect to x, okay, of the integral from y to x of e to the t, cosine of e to the t dt, like this. Now, I'm treating x as if it's a variable. I'm treating y as if it's a constant. So how can I get you to see this? Let's just say you could find this antiderivative. Let's say you could, all right? Which right now we can't integrate that easily. But let's say we did, all right? If we integrated this, okay, the antiderivative of this, okay, whatever that is, let's just say it's this block right here. That's the antiderivative of this. What we would do is we would then plug in x and y into this, right? So we would get the antiderivative of this is here. Plug in x, we get something, plug in, and then subtract from that what we get when we plug in y. So it would look like this. It would this be with x inside here minus that antiderivative with y inside there, if that makes sense. All right, now if we are going to be looking at this expression, which is what's in the parentheses here, if x is a variable, right, because we're doing the partial with respect to x, which means we treat x like the variable and y like a constant, then when we plug x in here, we're going to get an expression, right? It's going to be an expression in x. So I'm going to have, some function of x in there. If I plug y into this, I'm going to have some expression in y, but it's going to be a constant. The whole thing should be a constant because I'm plugging in a constant into this, not a variable. And now what I do, okay, because that's everything in the parentheses, now what I do is I take the derivative of this. And if I take the derivative of this, This is a constant. It's going to go away. And what I'm doing is taking the derivative of this box, but with x plugged in. So the derivative of this box takes you back to this, but with x plugged in. So all you get is cosine of e to the x. And that's it. I hope that makes sense. Let's try it the other way. Let's do the partial with respect to y. So if we do the partial with respect to y, of this integral, same exact setup. Then, again, now let me go back up here and, what we would do is we would find the antiderivative of this. The antiderivative of this would be this box, whatever it is. We plug in x, we plug in y, we get this. This time, it's going to be reversed because we're doing the partial with respect to y. Y is the variable, x is a constant. When we plug x in, this will be a constant, and this will be some function of x, or sorry, some function of y. So this is a function of y. And now what we do, okay, that's what's in this parentheses, we take the derivative with respect to y. So derivative of this is a constant, right? So the derivative of this is going to be 0 minus, now the derivative of this box takes you back to here, but this time with y plugged in. So what we get is cosine of e to the y, like that. And the 0 we don't need there, so we just get that. So those are the two partial derivatives. It's kind of an interesting problem. All right, let's do 21 because it has 3 variables in it. F of x, y, z equals xz minus 5 x squared y cubed z to the 4th. So first of all, what are the possible partial derivatives? So what are the things that we can find? Well, since there's 3 variables now, we can find the partial with respect to x, partial with respect to y, and the partial with respect to z. If we find the partial with respect to x, what we do is we treat y and z like constants. Partial with respect to y, we treat x and z like constants. Partial with respect to z, we treat x and y like constants. So I'm going to come up here and do this one first, remembering that y and z are constants. Z is a constant, so I'm going to cover it up. Derivative of x is 1, so you get just z. Minus, now, remember, x is our variable. This whole thing is a constant, everything. Y cubed, z to the 4th, that's some constant. I'm going to cover it up. Derivative of this right here is going to be 10x. But it's also, sorry, minus 10x. But it's then also times that. So I'm going to put minus 10, and then remember the x, because we brought out the 2, so x. But then times this, which is a constant. So y cubed, z to the 4th. And that's it. So you don't do product rule or anything because these aren't variables, right? You just cover them up and do your derivative here. Partial with respect to y. So we treat x and z like variables, constants. These are both constants, which means that's a constant. Derivative of constant, 0. We're treating this one and this one like they're constants, so I'm going to cover those up. Derivative of y cubed is 3y squared. The 3 comes out and hits that, becomes negative 15. So I'm going to have negative 15, and then this is going to become y squared, but we had x squared there, y squared, and then that one didn't change either, z to the 4th. On the last one, we treat x and y like constants. So over here, x is a constant, covered up. Derivative of z is 1, so we just get 1 times x. Here, this is all a constant right here. The derivative of z to the 4th, 4 comes out, so negative 20. And then we have this constant, x squared y cubed. And then this, we took the derivative of the 4 popped out, so z cubed. So there's number 21. double check these. Make sure I didn't make a little typo anywhere. Okay, we're good. $27 looks interesting. H of x, y, z, t equals x squared y cosine of z over t. Okay. So what are the partials that are, first partials that are possible? We have partial of h with respect to x, partial of h with respect to y, partial of h with respect to z, partial of h with respect to t. So there's 4 different first partials. If I do the partial of h with respect to x, I treat everything like a constant except x. So y times cosine of z over t, this is all one big constant. So I'm saying, what's the derivative of x squared? Well, 2x. So I'm going to put 2x and then times this constant, y cosine z over t. Done. That one wasn't too bad. Now let's do partial h with respect to y. So I treat the x squared like a constant. This is a constant. Cosine of a constant is a constant. So everything is a constant except that y. Derivative of y is 1. So it's basically gone, and all you have is everything else that's left there. X squared cosine of z over t. Wow. Okay, sorry about that. I don't know if I'll edit that out. All right, where were we? Taking the partial with respect to z now. Okay, so look, z is in our trig function. It's our variable. T is a constant. X squared and y squared are constants. So x squared, y squared, I'm just going to bring those down because they're constants. And they're attached to my function. So they're just going to come along for the ride. And I'm going to focus on taking the derivative of cosine of this. So let me rewrite this. This is like cosine of 1 over t times z. And t is a constant. So 1 over t is a constant. And that's a constant in front of z. So just remember that, all right? That's just a constant in front of z. Now, what is the derivative of cosine of something? Well, negative sine. So how about I throw that negative on the outside? Negative sine of whatever's in there, z over t. But then chain rule times the derivative of what's inside. So that's why I'd broken this apart. What's the derivative of what's inside if z is the variable? Well, 1 over t is a constant. Cover it up. Derivative of z is 1. So you just get 1 over t. So 1 over t. I don't think I'll clean that up anymore. I'll just move this, make some space for that negative. So there we go. Okay, so now with t as our variable and everything else is a constant, what I can do is I'll use this again because this will work. This is a constant, so I'll just put it here, x squared y. Now, derivative of cosine of something is negative sine, so I left some space there for my negative sine of what's inside, z over t. But now the derivative of what's in here. Now it's a little different because z is a constant. 1 over t is a variable function. So z is just going to be covered up and come along for the ride when we take derivative. Derivative of 1 over t, remember, that's the same as t to the negative 1. So derivative of that is going to be negative 1 over t squared, but then times z. So I'll just tack a z on top of this. So times negative z over t squared. And that negative actually out here can come out here and it turns this to a positive. So that is dot. The book actually takes it one more step. They just like bring this out here and just put this over t, which you can do. And then they take this over here. They tack the z on right here, and they put it over t squared, like that. That's just algebra case. Okay, next one. I liked 29. 29 looked good too. U is equal to square root of x sub 1 squared plus x sub 2 squared plus x sub 3 squared plus dot 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 plus x sub n squared. What does that mean? So what this is saying is that u is some function of the variable x1, x2, x3, xn. So there's actually n different variables, but we're just using subscript instead of x, y, z, right? Because eventually you kind of run out of letters. You only have 26 letters in the alphabet to work with to begin with, but what if you have 100 variables? Well, this is a better way of notating 100 variables. You just subscript them. You'll never run out of numbers. So we have all these partials. So we need to figure out what the partial of u with respect to x1 is, partial u with respect to x2, partial of u with respect to x3, all the way to partial u with respect to xn. Oof, that's a lot. All right, so let's try this first one. First thing we realize is that we're going to treat everything like a constant except x sub 1. So that's the only one that's a variable. Everything else here is a constant. And let's try a derivative. So what is the derivative of the square root of something? Well, from Cal 1 we know it's 1 over 2 times the square root of whatever that something is. So x1 squared plus x2 squared plus x3 squared plus plus dot 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 plus x sub n squared. Okay, that's a derivative of the square root of something. Times, chain rule, the derivative of what's inside. Everything from here on is a constant. So derivative of each one of those is 0. Derivative of this is just going to be 2x1, x sub 1. These 2's cancel. And so all you get is the x sub 1 over this. So I'll just move it. You just get x sub 1. That 2's gone over that. Now let's think about what would happen if I try this for x sub 2. For x sub 2, the first thing you do is take derivative of the square root, which is going to be exactly the same thing we had earlier, 1 over the root, 1 over 2 times the root. Then you go in and you take derivative of the inside. That's a constant. This is a constant. Everything after it's a constant. This one is the variable. Derivative of that is 2x sub 2. So then you get the same pattern, and the 2's would cancel. So you get x sub 2 over the square root of all this junk right here. And then this next one would be, by following that pattern, x sub 3 over that junk. And then the last one, of course, following the pattern, would be x sub n over the square root of all that junk. So that one we actually didn't have to take n derivatives. We just noticed a pattern. So what you could say here, there's a couple of ways you could say this. If you're trying to give me like a general answer, you could write something like this. The partial of u with respect to x sub k, the book uses I, but I'm going to use k, is equal to x sub k over the square root of x sub 1 squared plus x sub 2 squared plus x sub 3 squared plus dot 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 plus x sub n squared. There, like that. Okay, so if you replace k with 1, then you get this one. If you replace k with 2, this one, this one, this one. So you'd say something like where, k is an element of the list of numbers 1, 2, 3, all the way out to n, something like that. All right, that's probably okay. I'll let you do, you should try 30. 30 is similar to that one. Okay, how about 31? So for 31, f of xy equals natural log x plus square root x squared plus y squared. All right, and they want you to find partial of f with respect to x at 3, 4. So that means they want you to find the partial with respect to x first, then plug in 3 for x and 4 for y. So let's work first on getting the partial with respect to x. This will be equal to, well, we're treating y like a constant. So those x's are variables. So first of all, what's the derivative of natural log of something? It's 1 over the something. Okay, times now derivative of what's inside. Now we have two terms, so I'm going to do each one. So derivative of x, well, x is a variable, so derivative of x is 1 plus derivative of the square root of something is 1 over 2 times the square root of x squared plus y squared times the derivative of what was in here, derivative of x squared is 2x plus the derivative of y squared is 0 because y is a constant because we're doing partial with respect to x. So the derivative of the inside of this is just 2x. So I'll put that there. These two's cancel. And I'm just going to leave it like that. Okay, and I'm actually going to just plug in now. What's partial with respect to x at 3, 4? So let's see. Come over here and let's replace all my x's with 3's, all my y's with 4's. So 3 plus square root, 3 squared is 9, 4 squared is 16, times, in parentheses, 1 plus, let's see, this is really just an x on top, so 3 on top, and then the 2's canceled, right? So square root of, we just did this, 9 plus 16. So we get, let's see, over there, 1 over, this is 25, square root of 25 is 5, so 3 plus 5 is 8, so I have 1/8 times over here, 3 over, this is 5, right, because square root of 25 is 5, so 1 plus 3/5. And then, running out of room here, this is 1/8 times 1 plus 3/5 is 8/5. These 8's cancel, we get 1/5. Now, what this represents, okay, so just to give you, to make sure we're clear on this, if we were to go and graph this thing and look on the domain 1, 2, 3, and on the ground 1, 2, 3, 4, there's our point. We're plugging it into the function, right? And the function is some surface sitting up here. And we're going up and we're finding the point on the surface. And we're pointing ourselves out on that surface. If we're standing on it, we're looking out in the same direction that is parallel to the x-axis. And what we're discovering is that at that point, the slope of that line is 1/5, so it's pitched up a little bit. So if I were actually standing on that point, looking out parallel to the x-axis, and I was looking, and if I were to try and take a step forward there, it's a positive number, so I should be going up there. So the function in front of me should be sloping up. Not much. 1/5 isn't very steep, but it is up. It's not down. All right. 37. Now 37 asks you to use a calculator or graphing utility. I don't really necessarily want you to do that. I feel like I'm missing something. No, that's it, 37. F of xy is x squared y cubed. It wants you to find a couple of things here. And that's what I want you to do. I don't really want you to worry about the graphing. Although I invite you to go to Wolfram Alpha and do it. Try and take a look at them. So we're going to find this, partial with respect to x, partial with respect to y. Then, oh, that's it? Oh, that's kind of boring. All right, well, I thought this wanted the second partials. That's going to come on later problems. Oops. All right, this is going to be easy then. Partial with respect to x, this is a constant, so derivative of x squared is 2x, and then you still have the y cubed. Here, treat the y like a variable, x is a constant, so leave that alone. Derivative of y cubed is 3y squared. So 3 will come out in front of the x squared, y squared. That's it for 37. Sorry. Boring. All right, let's look at 39. Use implicit differentiation. So we have x squared plus 2y squared plus 3z squared equals 1. That's a quadratic surface. See, the problem is, though, we cannot solve for z explicitly. If we try and solve for z, we're going to get a square root and we're going to get a plus or minus. We're going to have two different functions. So this is not a true function of two variables. But we know this is a quadratic surface. We looked at these before, all right? Ellipsoid here, if we were to graph it. So either way, let's move on. We want to find, they want you to find the partial of z with respect to x. So they want partial of z with respect to x, and they want the partial of z with respect to y. I believe that's all they want, right? Yeah. Okay, so let's start with partial of z with respect to x. So what I'm going to do is I'm going to go through, I'm going to take the derivative with respect to z, the partial derivative with respect to x on both sides of this equation. So what that means is I'm going to treat x like my variable, y like a constant, and z like it's a function of x. So when I do this, the derivative of x squared will be 2x plus the derivative of 2y squared, since y is a constant, is going to be 0, plus, now the derivative of this, 3z squared. 2 comes out, so 6z, but here's the difference, times chain rule, the derivative of z itself. Now the derivative of z with respect to x is going to be the partial of z with respect to x. And then that's it for the left side. Derivative of the right side, derivative constant is 0. So now what we do is we try and isolate this partial. So I'm going to move this to the other side. I'll divide through by 6z. Partial of z with respect to x is negative 2x over 6z. So partial of z with respect to x is negative x over 3z. So what this is saying to us is that if you want to know what that partial derivative is, okay, with respect to x, if you want to know like that slope of that tangent line, you need to not only need to know your x coordinate, you need to know your y coordinate of the point on the surface. And then we can talk about it. But you have to have both of the points. Where did that thing go? Where's my rag? Huh. Where the heck did it go? Okay, I'm going to feel like an idiot. It's going to be like right in front of me somewhere. Did I leave it in my office? I think I left it in my office. Be right back. You try the next one. Rag. But I did. Oh, shit, it's right underneath my book. Idiot. All right, so let's finish this one up. I'm losing it, man, losing it. Okay, partial of z with respect to y, so I'm going to treat that like a constant, that like a variable, that like a function of y. So derivative of x squared is going to be 0. Remember, this is not equals. I'm just working this equation left and right. 0 there, derivative of 2y squared is going to be 4y, plus this is going to be the exact same thing, 6z, but then partial z with respect to y equals 0. So the only difference there on this one is this part. And then you move things around and solve and you get it. So that's it for that. Let's see. $45. I'll let you think about 39 yourself. Okay, I'm going to do, let's see, microphone, oops. Make sure I got this thing on, plugged in. Looks good. Okay, so I'm going to do I'm going to skip 43, let you do 43 on your own. Look at number 45. So we have the function of two variables, f of x, y, equals x cubed y to the fifth plus 2x to the fourth y. We're asked to find all the second partial derivatives. So that means we want to find these four things. Partial of f with respect to x and then x again. Partial with respect to x then y. The partial with respect to y then x. And then the partial with respect to y and then y again. So we want to know what those are. So let me start off by first finding out what's the partial of f with respect to x. So I'm going to treat all my y's like constants. That's a constant, cover it up. Derivative of x cubed is 3x squared. And then bring the y to the fifth in. Okay, plus, now again, covering up the y because it's a constant. Derivative of 2x to the fourth is 8x cubed. But then we have y still, because it was our constant. So that's our partial with respect to x. Let's go ahead and find the partial with respect to y while we're here. Partial with respect to y would be, cover up the x because it's a constant. Derivative of y to the fifth is 5y to the fourth. So 5y to the fourth, but I still have an x cubed there. And then over here, 2x to the fourth, that's all a constant. Derivative of y is 1, so I'm just going to get that constant. Plus 2x to the fourth. Okay, now, I'm going to try and find these four things. So what would partial of f with respect to x, then x again be? Well, that's the first partial, so I want to take, with respect to x, I want to take the derivative of that again with respect to x. So cover up the y to the fifth. This is going to be 6x. And then I still add the y to the fifth. Plus, again, cover up the y here. Derivative of 8x cubed is 24x squared. But I still had the y because it was a constant. So that's my second partial that I'm trying to find. Let me do partial of f with respect to x, then y. So start with this and then take the derivative of this with respect to y. So this time, x is a constant. So cover this up. Derivative of y to the fifth is 5y to the fourth. The 5 comes out, hits this. So we'll have 15. The x squared stays there. This power came down, y to the fourth. And then over here, cover up the 8x cubed. Derivative of y is going to be 1. So derivative of y is 1, so we just get plus 8x cubed. See what that is. Okay, student. Okay, so now we're going to do, let's do partial f with respect to y then x. So that's this one right here. We're going to take now the derivative of that with respect to x, which means that y is a constant. So cover this up. Derivative of x cubed is 3x squared. So 3 comes out. It becomes 15x squared but we still have y to the fourth. And then over here, we're taking the derivative with respect to x now, so this is all a variable, so it'll become plus 8x cubed. Hey, these are the same. Interesting. All right, now next one, fyy, would mean we take the partial with respect to y, which is this one, and then with respect to y again. So forget this is here. Derivative of y to the fourth is 4y cubed. The 4 comes out, hits the 5, so we'll get 20 x cubed, and then the y is now y cubed because power came down. Plus, now this is all a constant because we're treating y like the variable, x like the constant. So that's just plus 0. So that's it. Those are your second partials on that. All right, let's look at number 51. We want to verify Clairaut's theorem. So we're going to take a look at a function. U is equal to x to the fourth y cubed minus y to the fourth. Oh, by the way, I'm not doing number 47 and 49. I'm going to let you do those. Same principle as number 45, but they're a little more complicated. For this one, I want to verify Clairaut's theorem. So I don't know if I'm going to actually go through this. I'm just going to tell you what you have to show. You have to show that the partial of f with respect to x then y is equal to the partial of f with respect to y then x. So that if you do these different orders, right, partial with respect to x first then y, that should be equal if you do equal to doing the partial with respect to y then x. And there were some conditions in the theorem. You know, you had to have that this was a nice continuous function on a closed or on a disk or something like that. And this is a continuous function, two variables, because it's polynomial. So we know that polynomial functions in two variables are continuous everywhere. So this should work. So just go through and take these second partials and show that they're equal to each other. All right, number 53. We have f of xy equals x to the fourth y squared minus x cubed y. And you're asked to find f x, 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 and then f x, y, x. And I'm just going to do one of these. So I'll do this one. So what we're going to do is first we're going to find the partial with respect to x. Okay, so we start here. Partial with respect to x here is 4x cubed y squared minus 3x squared y. And then if we do the partial of that with respect to y here, 2 comes out, so we'll get 8x cubed y minus, with respect to y here, this right here is our variable, so that's a constant. Derivative of y is 1, so we just get negative 3x squared. And now if I do the partial with respect to x again, so we did the partial with respect to x, then partial with respect to x, then y is this one. And now we're going to come in and do that answer with respect to x. So 3 comes out, we get 24x squared y, because y is a constant. And then derivative of this with respect to x, which is negative 6x. So this is it right here. All right, number 58. They're asking you to find, well, that's just trying to get you to understand some notation. So I think that's, again, one of those ones I think I'll let you do on your own. See if you can make sense out of the notation there. And is that it for this assignment? I believe it is. All right, so I'm going to stop the video.